So we'll jump into these this last half here. Okay, so we're on the next proof. It says it's given that that ray BD bisects ABC. So we know that if the array is bisecting an angle, we have an angle bisector here. So we know that this is splitting this into two congruent parts. But that's what bisecting an angle does, and what a bisector means, right? All right, but we know that this first part, again, I already read that, but that is, of course, given as far as the proof goes. The next part here is, well, I just said that if BD is splitting angle ABC in half, that means that angle 1 and angle 2 are congruent, which is the next step. And how did I know that? Because that's what bisect means. So that is literally the definition of an angle bisector. That's what it means. Okay? Then hopefully we see these. Well, how did I know 1 and 4? Let's look at 1 and 4. Oh, 1 and 4 are congruent because those are vertical angles. So that's a case of VAT. And just double check, 2 and 3 also are congruent because of vertical angle theorem. That is true. They're vertical angle theorem. That's what VAT stands for. Vertical angles are congruent. All right, and then finally, this is very similar to the last couple steps in that, well, if I'm saying, well, 2 is congruent to 1 and 1 is congruent to 4, therefore 2 and 4 are congruent. Well, that's, again, a transitive property of congruence. I'm chaining congruency statements together. And then finally we have, well, if 2 and 4 are congruent and 2 and 3 are congruent, well, that must mean 4 and, well, so let's read it like this. 4 is congruent to 2 and 2 is congruent to 3. So 4 is congruent to 3. And again, that is the transitive property of congruence. No big deal. Looks bad. Let's do that again. Okay. And then, well, now we know that 3 and 4 are congruent. Like, now we know for a fact that 3 and 4 are congruent to each other. And so then it says I can conclude that this actually is bisecting this angle, this ray BG, right, is bisecting this angle FBH. And again, that makes sense because if these are congruent, that means it's bisecting. So if I have two congruent angles that are adjacent, then the common ray there in the middle is going to be a bisector. So that's what it's saying. And again, that's because that's by definition, that's what an angle bisector is that it splits an angle into two congruent angles. So if I have two congruent angles that are adjacent, they must have an angle bisector between them, and sort of vice versa there. All right, let's look here. It says that angle 3 is a right angle, and we want to prove that 4 is a right angle. Now we probably would look at that and sort of understand this, but we want to sort of go through the steps of proving this. So 3 is a right angle. That is given. And so why is the measure of angle 390? Well, again, that's what right angle means. It's the definition of a right angle. Right angles measure 90 degrees by definition. That's what they are. Okay, how do we know 3 and 4 are supplementary? Well, again, I'm looking at this diagram here, and I know 3 and 4 just by looking at them are a linear pair. And then because I can jump from the fact that they're a linear pair to that they're supplementary because of the linear pair theorem. All right, and then if I know they're supplementary, I know that they have to add to 180, and that's just the definition of supplementary angles. Because that's by definition what supplementary means. They add to 180. And in this case, well, it looks pretty similar to the previous step, except the only difference is that instead of 3, 90 is here. And that's because, again, I know 3 and 90 are the same thing, so we replace this with, this with 90 to get this step, so that's just going to be substitution. Property of equality. And so how do we know the measure of 4 is 90? Well, all we did is take this equation and subtract 90 from both sides. So we're just solving the equation. So that's just, we're subtracting the same thing from both sides. That's just subtraction property of equality. And then, well, if the measure of angle 4 equals 90, that is what a right angle is. So that's a definition of a right angle. My O's are weird. All right. So let's do the next couple. 3 looks like. These are maybe shorter. I don't know. All right, probably not. Angle 1 and angle 2 are complementary. We're trying to prove 2 and 3 are complementary. So if angle 1 and angle 2 are complementary, well, that's given. They gave that to us. Thank you. Well, if they're complementary, that means they add to 90. So what we're doing is we're saying that their measures add to 90. Measure of angle 1 equals plus the measure of angle 2 equals 90. So that's just the definition of complementary. Complementary angles, that is. All right, then we know that we're trying to say that, well, how do I know? Well, it says that 1 is congruent to 3. Angle 1 is congruent to angle 3. Oh, look, those are actually vertical angles. And so I know they're congruent because their vertical angle theorem says that. The vertical angle theorem says that all vertical angles are congruent. Well, if they're congruent, then their measures are equal. That's just the definition of congruent angles, right? So if their angles are congruent, they have equal measures. That is the definition, and vice versa. And then finally, we have with the measure of angle 2 plus the measure of angle 3 plus the measure of angle 2 equals 90. Well, that looks like this equation up here. The only difference is that we replace the measure of angle 1 with the measure of angle 3, and I can do that because they're equal from step 4. So that's just I just replaced it one with the other. So that's substitution, property of equality. And then because 2 and 3 add to 90, by definition, they're complementary. 2 and 3 are complementary because they add up to 90. So again, that is the definition of complementary angles. So we can do it both ways, going from, hey, they're complementary to that they add to 90, and also if their measures add to 90, they have to be complementary. All right, so we got some blanks here. In this case, we know 1 and 3 add up to 180. That is, of course, given. First reason, not so bad. Then it's saying the definition of supplementary angles. Well, again, if 1 and 3 equal 180, then angle 1 and angle 3 are supplementary, because that's what supplementary means, which it tells me the definition of supplementary angles over there. Good. And so if I know 1 and 3 are supplementary, and I know that 3 and 4 are supplementary because I can look at the diagram, they're a linear pair. So we use the linear pair theorem to say, hey, they're a linear pair. I see that, therefore they're supplementary. So I could do that. Well, angle 3 is congruent to angle 3. Well, that's just sort of saying, hey, you know what? It's congruent to itself. So that's reflexive property of congruence. And then finally, we use the congruent supplements theorem, which the congruent supplements theorem says, hey, you know what? If 1 is supplementary to 3 and 4 is supplementary to 3, that must make 1 and 3 congruent. So that is what we're trying to prove. And even if I didn't really understand this last step, I would still be able to know it because, again, it should always be what we're trying to prove. But that's why, right? It is saying that these two things, angles 1 and 4 are both supplementary to the same thing. Therefore, they have to be congruent. That's what the congruent supplements theorem says. And basically the same thing as a congruent complements theorem, except they'd be complementary, not supplementary. All right, finally, we have the last one. We know that it says that this bisects this angle, so that, that was a given. So if it bisects it, splits it into two congruent angles. And so we say that angle 1 has to be congruent to angle 2 because that's what angle bisectors do. They split an angle into two congruent angles, two smaller angles. So a definition of angle bisector. And then we have angle 1 is congruent to angle 3. That actually is a given statement. So it just goes to show you that just because it doesn't have to be all the givens at once up top. They can be, and sometimes they are, but not always. And then finally, we're saying, well, if 2 is congruent to 1, and 2 is congruent, and 1 is congruent to 3, well, that means 2 is congruent to 3. So again, we use the transitive property of congruence here. All right, sounds good. Proofs.